matches the Higgs excitation. In fact, this Higgs is even tunable in cold atoms. But so this idea of universality has been taken to a new level, as we know, by Richard Feynman, who suggested that we can use it as the basis of quantum simulations. And one of the active research directions in the last 2 years has been simulation of the Fermi-Hubbard model, which is commonly believed to be kind of the parent model for many strongly correlated systems, in particular high temperature superconductors. So I want to point out something special about experiments done with ultra cold atoms that has happened in the last 2 years, and this is the fact that several groups can now do experiments using quantum gas microscopes. And what this allows them to do is to measure every particle in a many-body state. So what you can see on the left, like these blue and red dots, it's not like a theorist conception, it's a result of an actual experiment. So in the Fermi-Hubbard model, every site in the lattice is being measured, and we know on a given site whether they have spin-up fermion, spin-down fermion, or an empty site. So in some sense, we can compare this to the style of painting known as pointillism, where instead of continuous brush strokes, they used individual dots. So now the kind of information that we get from about many-body states about the Fermi-Hubbard model is such pointillist style pictures that consist of quantum dots, and my talk will sort of discuss how we can analyze this type of data. And obviously, this kind of data that comes in the form of pictures is very inducive to use tools of machine learning, and I'll comment on this as well. Okay, so this is an outline of my talk. I'll spend most of my time discussing quantum simulations of the Fermi-Hubbard model. I'll try to convince you that some of the latest experiments, or recent experiments, suggest very sort of support the idea of magnetic polarons or kind of the motion of dopants in the Fermi-Hubbard model in terms of QCD-like picture of mesons. I'll then talk about what happens as the Fermi-Hubbard model is doped further, and how it goes from this polaronic liquid into a Fermi liquid state. I'll show you a recent observation of pairing due to magnetic interactions in the Fermi-Hubbard type model. As I said, comment on the use of machine learning tools to analyze snapshots. And then toward the end of my talk, I want to give an example of how simulations can also be used to provide insight into problems which are outside of the traditional physicist domain, but so that hopefully we can do something useful to kind of a broader society. Okay, so let me start by talking about the 2D Fermi-Hubbard model, and I will not give an introduction, an extended introduction, just to remind you, it's a lattice model where fermions can only hop between neighboring sites, which is schematically shown here. When two fermions meet on the same site, then there is strong repulsive interaction U. And one effect of this, one ubiquitous phenomena in these Hubbard type models is a tendency towards antiferromagnetic ordering. Let me illustrate it with a simple example. Consider two fermions and neighboring sites. And as we said, U is very large, so double occupied sites only appear virtually. And so we can imagine that if spins of the two fermions are opposite, then one of the fermions can hop on the neighboring site, creating a virtual double state and then hop back. But such virtual hopping is completely forbidden if spins are parallel. And so this effective kind of tendency towards anti-parallel spins can be described by this antiferromagnetic SISJ interaction. And so in theoretical analysis, what one often does is that actually one sort of gets rid of these states with double occupancy and uses the so-called TJ model, in which we retain antiferromagnetic exchange interaction, which originates from these virtual doublons. But then in the kinetic energy, we'll put projectors on the hopping. And so some of the numerical results, which I will show you, will rely on this TJ model, which is just the limit of the Hubbard model at large U, and it's easier to analyze numerically. Okay, so let's start with a simple question. If we introduce a charge carrier in an antiferromagnetic state, what happens? So let's, yeah.
Just to get the questions going.
Sure.
Is the boundary condition just a sharp boundary condition, or is there a potential near boundary that changes?
It depends on which experiments. Now there are experiments with hard walls, experiments like usually for the type of thing that we're describing here, say Mott insulators, this doesn't matter because you have a plateau in the filling factor. So then we would have to discuss specific experiments. Usually there is a potential, like usually it is parabolic, but then there are, let's say in the group of Marcus Greiner, there is a special potential which allows to cool better, which is not parabolic, it creates metallic states. So it's the beginning of a long discussion.
Okay, thank you.
But for things that we discuss, usually it will not matter. But it is one of the tools available for kind of optimizing system properties. Good, yes, please interrupt with questions. Right, so now let's start with a hole, and now let's imagine that it starts moving, right? Okay, it moves by one side, by two sides, and notice something remarkable happens. That before the hole started moving, we had perfect antiferromagnetic arrangements of neighboring spins, but now we generate some like spin configurations in which some of the nearest neighbors are ferromagnetic. And of course, this is not favorable from the point of view of magnetic exchange interactions. And so as a result, if we think about how a hole moves away from the site where it originated, it creates a kind of a linear potential. So this idea has been pointed out early on by people like Daniel Chomsky, Bob Laughlin, and others, and they suggested that we should think about this picture kind of by analogy with spin charge separation in 1D, where we know that there is a spin carrying soliton and a charge carrying called spinon, and then there is a charge carrying soliton called holon. But the difference in 2D is that there is a linear potential which binds them, so they do not separate, but rather the system behaves as a kind of bound state. And of course, this is reminiscent of what we remember from QCD, where mesons consist of pairs of quarks, which are also confined by a linear potential. Okay, but let us just talk about experiments. So what do they see when they put a hole? Okay, and in this case, experiment was done with doublons, but for the from a Hubbard model, one can prove mathematical theorem that doping with holes and doublons is exactly the same thing. So I'll kind of show interchangeable experiments with doublons and holes. So what you can see is, and this experiments from the Munich group. So there is it's a Mott insulating state, and they introduce just one doublet. And this doublet is free to move anywhere, right, in this field of basically in the system. But when they characterize magnetic correlations, what they plot is they plot spin correlations relative to the doublons, because we expect that spin correlations like this magnetic dressing will always occur in the vicinity of the doublet. That's why in this picture you can see that the doublet is put in the center, but in reality the doublet could move anywhere. And if we look at just nearest neighbor correlations, okay, notice that they are all sort of negative, meaning we still have antiferromagnetic correlations. And let's say far from the doublet, they recover the kind of value that they would have without any doublet, and then they get somehow suppressed, somewhat suppressed in the vicinity of the doublet. Okay, now let's look at diagonal correlation. So here, situation is much more striking. If you remember, like in a perfect antiferromagnet, so on the diagonal we have ferromagnetic correlation. Just spins should be aligned, and that's what we see far away from the doublet. We still see positive ferromagnetic correlations. But what happens next to the doublet? the correlations even changed sign, right? They became antiferromagnetic. So can we understand this? Well, actually, the picture is rather simple. So these experiments were done at a temperature which is not too low. And so like correlations decay with the distance. And so the strongest correlations were nearest neighbor correlations. And let's say before the doublet of the hole started moving, right, we had, so we said like this sort of perfect antiferromagnetic, well, okay, in cartoon, okay, I'm drawing it as a perfect, but it's like whatever is the thermal equilibrium of the Hubbard model, that's undoped Hubbard model, which had shown antiferromagnetic correlations nearest neighbors, ferromagnetic or next nearest neighbor, as long as there were no charge carriers. But now, as the hole moves, you see that the spins which used to be nearest neighbors are now on the diagonal, right? And so now if you look at diagonal correlations next to the hole, then we have to average over some correlations which are kind of the remainder of the original sort of not insulating state, but some which used to be nearest neighbors, and they were the strongest correlation. Now, just because of the hole motion, they became next nearest neighbor. And so when we average, actually we find that the signal is dominated by the bonds which used to be nearest neighbor, and that's how we recover the antiferromagnetic diagonal correlations. Actually, one can take this cartoon into an actual microscopic calculation, and the picture, like in the simplest case, we can start just by saying, okay, let's, so the spin can move, but it's very slow, like its motion is given by the scale of J, whereas the hole can move rather fast. So now if we want to represent the motion of the hole, we can think about it hopping, but notice that if it's like a simple single particle problem, like we can characterize an instantaneous stages by saying where the hole is. But here, that's not enough. We have to specify the trajectory, because the trajectory actually tells us about how magnetic correlations have been changed. And that's why when we represent the motion of the hole, we have to plot it on this beta type lattice. And so different sides of this lattice correspond to different trajectories. And so what we have is effectively a tight binding lattice with hopping and a linear potential that, as we said, as the hole moves, it creates a string of flipped spins. And we can then compare results of this model with experiments. So I will just comment on like cases that we discussed, and we have a mobile hole. And so this is, for example, nearest neighbor correlations, and that's what we saw, how these correlations sort of get weaker as we approach the hole of the Dublin in this case. So on the left you see experiment, on the right you see theory, and then sort of below you see diagonal correlations again next to the Dublin. So maybe it's something that is obvious to everyone, but let me point out that when we talk about this type of characterization, it's no longer a two-point correlation function, right? We're measuring correlation between two spins, but relative to the hole. So it's really a three-spin correlation, right? So it's, sorry, three-point correlation, one which carries a charge and two that carry a spin. And that's, of course, the kind of measurement that's not available in traditional solid-state systems. Okay. And also, sort of let me emphasize that when we do the theory, we do not start with an ideal classical antiferromagnetic state, but we start with, say, whatever correlations we have at a given temperature, at a given value of sort of exchange, either from Monte Carlo and Heisenberg, or just from experimental data on the undoped Fermi Hubbard model. Yeah.
Experimentally, can you really consider correlators you measure as equal time correlators?
Oh, it's exactly equal time, because you collapse the entire wave function.
So but you don't go side by side.
No, it's like you measure all particles at once. It's like real, like as textbook, you know, classical collapse of a quantum wave function. Good. Other questions? Okay, but then our colleagues became much more ambitious, and they decided to ask the question, well, can one actually see the strings? So remember we said as a hole propagates, it leaves behind the strings of flipped spins. Can we observe them in the data? And so this is the work really by Christy Chu and Annabelle Bort. So Christy at that point was a student in Marcus Breiner's group. So how the experiment is done? Well, actually, let me maybe make a disclaimer. So previously I showed you data from a manual blocks group, and they could, that time they could separately, they already could separately resolve spin up and spin down. In Marcus's experiment of 2 years ago, they could not resolve separately spin up and spin down. They had to choose whether they image spin up or spin down, but they had a colder temperature. So, but as you'll see, the fact that they have to use this sort of spin resolve measurement is not a showstopper. So here again is, and also another comment that if like on a given site there were 2 fermions, then again it's just a feature of the measurement, and actually it showed up as an empty site. Anyway, so let's say this was the actual sort of many-body wave function, but then when they do the measurement, they decided to focus on spin down, let's say, blue fermions, and so what they see is just blue fermions. And then they compare this given snapshot to the perfect kind of checkerboard configuration, and then sort of mark the difference. Right here, you can see that like these 4 sites were opposite to what they should be in a perfect checkerboard. These 2 sites are different. Like again, these 2, and so they we can then label them as a string of length 4, as 2 strings of length 2, and 1 string of length 1, and we can build a histogram. And then what we can do is just look at this the distribution of the strings, and what you find is that so the lowest point, sort of this is actually, these are the strings which you have even without doping. This just shows that, you know, we're not dealing with a classical antiferromagnet. We're dealing with like system that has thermal, that has quantum fluctuation. But now the points on top, this is what happens when they dope. And it looks like it's a slight change, but notice it's logarithmic scale on the y-axis. So like for longer strings, the probability to have longer strings goes by almost a factor of 10. And you can then ask, oh, but maybe we got extra strings just because we removed some of the sites. And you can check that it's not enough just by, so the yellow line is what would happen if we started with just, you know, the type of snapshots that we get at half filling and then randomly removed some of the holes. We see that we really get kind of a different distribution, like we have many more longer strings, which arises from the string motion. And this green line, it just shows you that you can describe this efficiently, uses this meson-like theory. Well, yeah, sure.
Why does the discrepancy only appear at long distances from short distances?
I think at short distances, you get a lot of strings, which is just exchange interactions, right? Because this naturally generates, you know, kind of strings of lengths too.
So what is that length scale?
Like, okay, so well, I'm not sure if you can rigorously define a length scale, but let's say if you look at the length, the earlier data that we discussed, you can see that the size of the polaron is about a couple of lattice constants. So it's kind of like of the order of the size of magnetic polaron. But yeah, okay, it's a good question. We did not really try to understand the kind of, like understand if there is a length scale that you can extract from the description. Yeah.
If you made experiments where they put 2 doublons, and can they see some effect of binding? Because if you take 2, you can hop without frustrating.
It's coming. Just wait. So okay, just yes, sure, yeah. Oh, it's just this model that we called, you know, that basically you have a spin and a hole and then they're bound, and as they move around, they sort of mess up spin configuration. I mean, I don't think even we called it, like the name goes further back.
So it relates to some extent maybe to geometric frustration.
Yeah, I guess you can say that you generate something that looks like frustrated spin configurations, not in a sense that you actually have frustrated interaction. It's just like a moving hole, indeed, kind of scramble spin configuration. Obviously, we don't, I mean, so there is a string, but we don't want to call it string theory. So. Other questions? Okay, yeah, thank you for the questions. Okay, but just like on the theory front, like one thing that once you take this meson like model seriously, you can make interesting conclusions. Some of them have been made before. So if we're saying that, okay, look, we have a particle with a linear potential, it reminds us of a Stark ladder problem, right? Like a particle in the presence of electric field, and just by dimensional counting, we know how to get like energy scale. And so this corresponds to vibrational excitation of such mesons. That, again, this argument has been done some time ago, and evidence for such vibrational excitations has been seen in numerics. But in fact, if we look at QCD, there is another type of excitation that we can also, like, there are mesons which have the same quarks and they only differ by quantum of angular momentum. Therefore, in this geometrical stream, you can also check, well, can we have this rotational type excitations? And in QCD, it's like this Regge formula tells us how energy of such kind of high angular momentum state changes with angular momentum. And so now you can think about this type of excitation is that when we take this bound state of a spin and a Holland, but we sort of consider a wave function that has an non-trivial winding when we rotate by half, let's say, changes a minus sign to get a d wave. And this numerically, by looking at ladders, you can see that indeed this approach seems to work. If you, okay, so the bottom, this is somewhat technical, but this is basically the spectral function. That's what we're used to being measured in RPES. And this peak is the usual kind of quasi-particle in the Fermi-Hubbard model, in the TJ model. But you can also make an excitation that corresponds, that basically gives the initial configuration a finite angular momentum. You immediately see that the spectral peak in the spectral function shifts to a different energy. So even if you say can have some people obviously may have doubts about the validity of this geometrical stream approach, but this is honest numeric, and it shows that there is indeed a rotational excitation that has kind of the type of scaling that with say exchange interaction that we would expect based on geometrical stream model. Yeah.
Why is the amplitude of the peaks so much lower than the?
Because we can, because you see, it's not easy to construct an operator that would really create like an eigenstate of this rotational excitation. So we did something that's physical, that can be realized in some kind of, let's say, pump and probe RPES type experiments, or experiments with modulation of optical lattice. But so it has a finite overlap, it has the right symmetry, but the weight is not perfect. Thank you. Questions? Okay, so far we talked about basically individual polarons, what happens when we have several of them, and let me point out one of the features that has come up from recent experiments in cuprates, and this is this crossover that doesn't depend on the temperature, but seems to separate kind of a behavior that's happening at smaller doping from the behavior that's happening at larger doping. There are different types of signatures. I'll just mention one that, let's say, in the kind of high doping regime, we see that the quasi-particle weight does what we expect it to do. It increases with lowering the temperature, whereas in the kind of lower doping regime, actually the quasi-particle weight goes down with lowering the temperature. So what I want to show you is that essentially the same crossover can now be seen in experiments with cold atoms, and in fact it can be understood from the picture of crossover between this magnetic polaron, picture liquid of polarons, to more from a liquid type behavior. Okay, yeah.
So, is there anything like strange
I'll show. Let me first show you the data. But in fact, like so okay. I will not talk about, there have been transport measurements, and they have seen like basically something that's analogous to linear anti-resistivity in this strange metal. At relatively high temperature, right? So still the temperature, as you will see in this experiment, it's roughly, you can say it's like what is shown here, it would be of the order of Néel temperature, right? But like this crossover that we're describing here, right, it actually can be seen even in cuprates at relatively high temperature. Good. Okay, so again, okay, I'll just highlight some of the data. So what you can see here is, again, what's being measured is just 2-point spin correlations, as a function of doping. And so the first ones are the sort of diagonal, right? So we know that at half filling in the kind of antiferromagnetic state, this diagonal correlation should be ferromagnetic. So you see they start being positive, but as doping increases, they change to antiferromagnetic. Then we take sort of again correlations which are 2 sides away, but in the horizontal direction, again, in classical antiferromagnet, we would expect them to be ferromagnetic. So they start being ferromagnetic, and then they change sign to become antiferromagnetic. Even longer range kind of correlations, which when we choose them like at half filling, they're chosen like, to be ferromagnetic, but as we dope, they become antiferromagnetic. And you see that this change from ferromagnetic to antiferromagnetic occurs around 30% doping. And in fact, the fact that at larger doping, correlation become antiferromagnetic is what we would expect from liquids, right? From liquids, it's Pauli principle, which dominates. We're much more likely to find opposite spins close to each other.
So these are equal time?
This is all snapshot, it's all equal time. So, okay, and then of course, 2-point correlation function, you can take a Fourier transform and look at how spin correlation function looks like as a function of doping, sort of close to half filling, we get a peak at close to pi. And then as doping increases, you see that actually like beyond the doping of around 30%, we get actually incommensurate peaks that we would expect based on simple, say just Linhart function or RPA type description, basically perturbative treatment of the interaction. And in fact, one can be quantitative in comparing, say, spin susceptibility like at small wave vectors, and we see that as we go to large doping, and then we start sort of decreasing doping the approach. Half filling spin susceptibility goes up, but then it actually saturates. So we don't yet see like a full spin gap, right? You know, like based on what we know from cuprates, we would expect a spin gap to appear. So this is more like a precursor of spin gap because probably temperature is still too high. But what you can tell is that if you try to model this data with just like RPA or some kind of more sophisticated versions of RPA, they work at higher doping, but they fail sort of at smaller dopings. They do not capture this saturation of spin susceptibility. Okay, so okay, there is maybe yeah. Okay, maybe let me yeah.
How do you know it's an equilibrium? Is there a test applied to check that?
You can look at different types of correlations, say between spin and charge. So, for example, in this case, what you can, like what we're looking at is, let's again a 3-point correlation, like spin correlations relative to a hole, and we can compare it to exact diagonalization. You see this breakpoint at this temperature. It looks reasonably well. So, and okay, so and now again, I just want to also emphasize that if we try to describe the behavior of the 3-point correlation function, so models like RVB or even PyFlux, they kind of work they work reasonably well at larger doping, but they fail. For example, they fail to sort of capture this change of sign of the correlation function at small doping, whereas say this geometrical string model that I told you about, like, so it works at small doping, but fails also around 30%. So somehow, like when we start from the perspective of weakly interacting magnetic polarons, we can describe the system up to around 30%, but then at higher doping, we're better off in terms of describing the data by using our traditional perturbative treatment of interacting fermions. So I think this suggests that this crossover that has been seen in condensed matter systems is indeed a crossover between this magnetic polaron type liquid and fermion liquid. Okay, but so then there was a question, so what about using these magnetic correlations to induce pairing? And of course the issue is, well, temperature is rather high, right? So if we just go by our analogy with cuprates, it's too high to see pairing. But of course, sort of given the insight that we have, we can, like theories could suggest a way around. And this is really the idea of Annabelle and Fabian to use a trick of mixed dimension. So in a nutshell, the idea is as follows. So let me explain it in the case of a ladder. Even originally, theoretical idea was given for a bilayer. But it's easier to illustrate in a ladder. Also, as you will see, experiments have been done on a ladder. So, okay, probably many of you know that if we have a ladder, it's like a piece of the Fermi Hubbard model, then when it is undoped, like a good cartoon of the system is that we get singlet configurations between fermions on these individual rungs. And then as we dope, then in order to minimize sort of frustration to this magnetic order, the holes will tend to come together, that they will be binding. So, but there are two things which actually, if we want to optimize this pairing across the rank, there are two things which we would like to do. So first of all, we would like to minimize tunneling in the transverse direction, and that's actually clear because if holes are far away from each other, then they can tunnel individually. They can regain some kinetic energy, right? Whereas if they're together, they cannot tunnel. On the other hand, obviously, this kind of singlet pairing is maximized by transverse exchange, by J-perp. And then, like naively, when we think about it, well, in order to get larger J-perp, you have to have larger T-perp. Of course, it never stopped theory. So people like Morris Rice, Heinz Scholl, they considered like theoretical models where J-perp was taken to be the largest scale. But actually, we can really do it in experiment. And the way to do it is to just apply a bias. So we want to apply the difference of the potentials between two chains which compromise a ladder. And so now, if this bias is large enough, then single particle tunneling is frozen out, right? Because it's no longer resonant. So it's switched off. On the other hand, now when this fermion tunnels virtual and creates a double occupied state, its energy will no longer be U, but U minus delta. So as a result, by adding this bias, we actually achieve two things. We get rid of T-perp of perpendicular tunneling, and we exchange J-perp, and both are good for pairing. And that's exactly the type of experiment that has been done by Sarah Hirst and collaborators in Munich. So what you see here is, again, this individual snapshots of fermions. This has been unresolved. And so obviously here you can see two holes that are sitting next to each other, right? So they make a pair. And in order to be quantitative about this, let's see, what is plotted here is a correlation function of the positions of holes as a function of distance. So when there is no bias, right? So this is this delta equal to 0, we find that actually two holes are unlikely to sit on the same run. However, when we introduce a bias, while we see that actually two holes are now more likely to see that there is an appreciable bunching of holes. And obviously in this case, right, so we're looking at a model in which the benefit of having two holes on the same run is purely magnetic. It's because this way the system has large J-perp, and therefore when holes on the same run, we can have the system benefits from strong J-perp, and when holes on different rungs, then yeah, this sort of benefit of magnetic correlation is suppressed. So it's not plain vanilla from a Hubbard model, but it's clearly hole pairing, which is driven by magnetic correlations.
Silly question, but why does this correlation function change sign when you turn on delta?
So that is something that, again, like we were all brought that ladders should have pairing. But if you look at the inside of this pairing, it's actually like these holes do not really sit on the same run. They're much more delocalized. Because physically, just you really like individual holes, they really want to benefit from T-perp. And that's why you don't want holes on the same run. So probably, therefore, we know that there will be pairing. But if you look at the kind of energy scale based on this kind of older papers, like Rice, like Troyer and company, the binding energy of pairs is much, much smaller, right, than this one.
So G is n minus expectation value n.
Yeah. Right. So basically the answer is that, okay, we would have to look not at the same site, we would have to look at slightly non-local correlations, and we would have to go to much lower temperature to see that pairing without the bias. But again, I think here it's a proof of concept that we see magnetically mediated pairing, and here sort of strikes you in the eye, you can see it in real space images. Yeah.
So in these pictures, there's no retardation.
It's honest from a Hubbard model, as honest as it gets.
Which is often crucial.
That's correct. So here, with this model, we really want to understand what is the ground state of the Fermi-Hubbard model. But of course, we know for cuprates, correlation length is size of Cooper pairs is small, so issues of retardations are much more subtle. But yes, so there is a kind of limit in terms of analogies between cold atoms in condensed matter systems. Other questions?
Yeah. Can I ask a question by Zoom? Do you hear me?
Yes. Oh, hey, Daniel.
Yeah. Hey. Actually, I wanted to ask this question just before you started to speak about mixed dimensional ladder. As to the regular Hubbard model, one hole is all fine. Now the question is about two holes, whether there is really tendency to pairing in a regular Hubbard model, not in this special mixed dimensional ladder. Because in principle, physics might be rather simple. One hole leaves a trace of wrong spins. The second hole moves behind it and repairs the damage done. So that it may give a tendency to pairing, like Cooper pairing. So third question, whether there is any tendency of this type in regular Hubbard, not in this mixed dimensional special thing. And second question, which probably may relate also to your problem. If there is a tendency to pairing of two holes, what about 3 or 4? Wouldn't they form clusters like 4 holes or 5 holes clustering together? That also relates to your mixed dimensional ladder, whether it's indeed only pairing correlation and what's cup interaction between pairs. Would they repel or would they attract? And there would be tendency for forming kind of pools, whole pools.
Okay, well, thank you for the question. So I think your first question was about 2D systems. I think it like honest 2D experiments that so far temperature is not yet low enough for us to convincingly say, oh, is there pairing or not? But obviously our experimental colleagues are going in that direction. In terms of interaction between whole pairs, and I can just show you that was exactly my slide. Next slide. So that's something that our colleagues looked at. Sorry, it's not unpublished. We'll slide it. At least it's unpublished, but it's on archive. So here you can see correlation functions, like again on a ladder when they introduce focals, and you can see that these kind of pairs tend to separate from each other. When they introduce 3 whole pairs, then again they separate. So now, whether this means that if we go to thermodynamic limit, we will have a crystal of the pairs, or we will have, or probably it's a Lagrange liquid, but which correlations will be dominant? Will it be more correlations that correspond to kind of a superfluid phase of these bosonic pairs or crystal phase? From these experiments, we cannot tell. It's only like 9 sort of sites along the ladder. Again, like based on the MRG, it seems like that CDW correlations would be stronger, like in this specific case.
Ladder in that sense might be somewhat special because it's essentially a 1D picture, so you can have something.
That's correct.
Think of Lagrange limit and so on. What about 2D?
Oh, as I said, Daniel, our colleagues are working on it. Unfortunately, temperature is still too high, but I think at least they can, hopefully what they will do relatively soon is to introduce the same trick of mixed dimension to bilayers. And then we'll have these pairs, let's say, in 2 dimensions. But they have, I mean, they're working on it as far as I know.
Okay, thank you.
Yeah, thank you for the question. Okay, so then maybe let me just briefly comment that on this idea that since our results of experiments and our images, we can use tools of machine learning. So if sort of convolutional neural networks can distinguish pictures of cats from dogs, so let them do something more useful and distinguish different theoretical models in high TC Coop rates. So as a comparison, we chose, well, it's real, Annabelle and Fabian chose two theories. Like one is the pi flux REV theory. I'm not going to the detail. It's some like for non-experts, some kind of mean field theory inspired by some spin liquid type states. And the other is geometrical string model. And then what one can do is one can train, and then so we have two ways of generating snapshots. So we have two theories, and then we also have experiments, and then we can ask these convolutional neural networks to learn and tell us which of these images they judge to be similar and which of them come out to be very different. So if you train kind of convolutional neural networks on these three types of data from the very beginning, let's say, so as I said, experiment and two theories, and what you find is that it's actually usually very confused between the geometrical string model, and here I'm talking about small doping regime, but it can very easily distinguish the pi flux theory, which says that at smaller doping, at least this geometrical string model is sort of provides a better agreement with experimental results. Or let's say another way of analyzing the data would be to, like at the training stage, the convolutional neural network only sees theoretically generated images, either geometrical string model or the pi flux model. And then we give it experimental images and ask to assign them. And you can see again for smaller doping, this convolutional neural network assigns images with a kind of higher probability to the geometrical string model than to the pi flux. And you can say, oh, it's kind of the effect is not so impressive, but I want to emphasize that it's based. This is a preference based on a single image, and a single image has a fairly limited information, right? It's most like 8 by 8. If we start adding like a few, let's say we give 4 snapshots and say, oh, they're from the same family, then this like 15% difference for one snapshot becomes like already 80% preference for the geometrical string model. But this difference between geometrical string actually gets sort of no longer works at higher doping. In fact, we have seen just by looking at correlation functions that sort of pi flux any kind of REB theories work better at larger doping levels. Okay, but of course, like convolutional neural networks are kind of black box models, but so here those are crucial insight. We collaborated with from Cole Miles and Unakim. They collaborated with Annabelle to really understand what type of correlations these convolutional neural networks pick up. And I will sort of not go through the details, but basically you can figure out that the type of kind of the minimum amount of information that the CNNs used to understand the images were kind of this 2x2 clusters. So this were 4-side correlation function. And in fact, you can see that for geometrical string, the type of patterns that they selected is exactly what we would expect on kind of on the kind of configurations which appear as a result of the whole motion, right? Throughout the whole motion, we see that, let's say, next to a hole, we have nearest neighbor spins which are ferromagnetically aligned. Okay, so do I still have a 10 minutes? Okay, so so far this was sort of simulation, which of course is an interesting physics problem, but I think one of the questions that we have been thinking is whether we can use quantum simulations to do something for the kind of broader community. And here I'll tell you about our work on NMR inference. And as I said, like the main credit should go to Dries Sals and Kushal Sastaram and our colleagues from Maryland. Okay, so maybe let me start with a few general remarks. So I'm sure all of you have seen a lot of excitement, or some would say even hype, about quantum computers. And probably kind of one of the kind of more reasonable comments was done by John Preskill. He said, well, in the near future, we should not expect perfectly working quantum computers that will do factorization of large numbers. We should really think about NISQ technology. So it's computers that have finite decoherence rate and that have finite number of qubits. And we need to find problems for which they are good. And another actually interesting comment that John made at a conference, he said that he expects that quantum advantage will first appear in problems which are intrinsically quantum. In fact, there is an interesting Twitter which rates various kind of statements about quantum computing as bullshit and not bullshit. So this comment got the rating of not bullshit. So motivated by so I'll tell you about something along these lines when basically what we want to do is sort of solve a problem which is relevant to our colleagues in chemistry, biology, medical sciences, which is if you have a spectrum, right? Basically, if you do an NMR spectrum on a system, and then you want to determine the underlying Hamiltonian, right? So, like specifically saying biomedical research, so you get an NMR spectrum, you want to know what exactly is the molecules that gives rise to it. But I'll just solve a more modest problem, which is, okay, well, let me at least from the spectrum tell you what is the Hamiltonian that gives rise to the spectrum, because this Hamiltonian already contains a lot of information about the underlying system. It knows about symmetries, for example. Let me point out that what's unusual is that experiments, NMR experiments in sort of biomedical sciences are done at room temperature, which is orders of magnitude higher than any kind of energy scales for NMR. Therefore, essentially, for us, it's like analyzing spin correlation function at infinite temperature. So therefore, like a technical problem that we want to solve is somebody gives us a spin correlation function. That's kind of our conventional spin correlation function, but computed at infinite temperature. So from the spectral function, can we tell what the Hamiltonian is? And okay, to kind of more experienced among us, this reminds a problem that our sort of mathematical physicists thought about in the past, whether you can hear the shape of a drum. And in that case, the answer was no, but there is a big difference. So like a regular drum it's a linear system. So basically like you get some basic frequencies, and then all the other frequencies, they just appear as additions, as integer multiples of those. But in an interacting many-body system, we do not have such addition of the spectra. In fact, we know that roughly the number of transitions sort of scales with the size of Hilbert space, so it's exponential in the number of spins, but the number of parameters that characterizes Hamiltonian is just polynomial. So therefore, the problem is actually over-defined rather than under-defined. Okay, so I will not. So the idea is that one can actually design a compute. One can actually design a kind of a quantum computing algorithm that compute the spectrum. And one thing you may be surprised is, well, but this is an infinite temperature. So how do we do this? Like, because usually in quantum computers, we know that we start with pure states. Well, the answer is that basically what you have to do is you sort of, it comes at a cost of doubling the number of qubits. And so therefore we sort of, if we want to simulate n spins, we need 2 n spins, but at the end of this quantum circuit, we can get the spectrum. And but then there are of course interesting questions just in machine learning. So like if you know let's say you obtain the spectrum, so whether you can actually converge to the Hamiltonian. So it turns out that the landscape is very rough, and therefore in order to converge, what you have to do is you have to start in the vicinity of the right Hamiltonian. So what Dries has done was to just look at, let's say, NMR data on molecules with 4 spins, which are relevant to actual like human human systems, and you can naturally sort of ask whether they do clustering, and you find that yes, they fall into four clusters. And actually, if you look inside, you realize that well, that there is something behind this clustering. Say like this spectrum, which looks like obviously has a lot of degeneracies, right? Because it has some few very high intensity peaks. This comes with molecules that have these methyl groups, whereas the spectrum that is to us looks the most like a chain. So this comes from molecules that have this benzene ring. And so the trick is really when you analyze, when you try to converge is that first when you get a new spectrum, you have to already know the clustering. So you have to start in the vicinity of the right cluster. Yeah.
Sorry.
Yes.
Just perhaps a nice question like this. Quantum circuit for green file spectrum, is it in any way related to phase estimation?
To do Fourier transform, it does, yes. Right. So the simplest way you can, right. So experiments that I'll show you later on, they will not yet do the step that where you do phase estimation type procedure to get the output in Fourier spectrum. So there, what we do, which is basically look at this correlation function, we evolve it in time, because you can get rid of this, but then you would have to measure this correlator for different times and then Fourier transform by hand. But you can sort of short circuit this by adding this. Yeah, exactly. Yeah, phase estimation. Yeah, thank you for pointing this out. Yeah. Okay. Yeah, I'm very close. So to concluding, so let me just here show you that. Like, of course, the real challenge now is to show that something can be done on real existing hardware, and this is really the beautiful work by our colleagues in Marcus Stevens and Chris Monroe's group in Maryland, where they simulated an NMR spectrum. It's a 4-spin molecule in zero field, which is usually much harder for inference for classical computers. And there were many technical challenges to overcome. And here, like, there was really hard work done. Kushal, who was my graduate student, he recently defended. So, like, in particular, if you just, because you know that the spectrum consists of a few sharp peaks, so naively you would need to do kind of many time measurements. So he came up with several tricks on compressed sensing, how with a limited number of measurements you can still get the correct spectrum. So here you can indeed see comparison of the actual experimentally measured spectrum and the one computed on an ion-based quantum computer. But what it allows us to do is, you can say, well, we don't, like, for spin, that's kind of simple, why do we care? But from this experiment, we can now ask the question, so what will be the requirement for us to be able to do NMR inference on molecules which are really relevant to current research, for which, let's say, doing classical inference is challenging. And here, I'll obviously I should, if you ask me, I'll give you the details. What are the limiting factors but the conclusion is that with infidelities of around 10 to -4, and if we can apply something 100,000 operations, we will be able to sort of do this sort of quantum computer-based inference on systems that are hard for classical problems. And of course, like, it's not yet within current hardware, current error rates like of the order of %, and we're talking about a few hundred operations at most. But our colleagues tell us that this is something that they can imagine doing in the next few years. And I want to emphasize that this approach does not require error correction, because what really is important is we only need to compute the spectra as well as the nature gives them to us, right? Because nature has its natural decoherence rate. We don't need the accuracy better than nature. That's why when we get this infidelity rate in number of circuits, we're sort of really doing computations which are sufficient for interpreting the data. Okay, so with this, let me conclude. I tried to give you a few examples of what can be done with quantum simulations. So firstly, by analyzing the Fermi-Hubbard model, which is dear to the hearts of many of us in this conference. And also, I think that there are very interesting problems outside of conventional condensed matter physics where quantum simulations will be useful. And I gave an example of NMR inference. Thank you.
general question following up. How much effort is ongoing in the community simulating strange way beyond the results?
I don't know how to quantify it. I mean, there are many groups which work from a Hubbard model. So transport experiments are probably not the most natural experiments for cold atoms, although so Wasim Bakr probably had the most impressive data. But again, usually, okay, we can talk more about it. Like you can attach leads and do transport like experiment. That's say what my colleague Tilman Essinger is doing at ETH. But let's say in these quantum gas microscopes, it's hard to put reservoirs. So, but what they do, they can say imprint a certain potential, then remove it and see how the system relaxes. So that's what Wasim Bakr has been doing.
Does it have to be transport?
Exactly. That's exactly. So like in this case, what they measure is how charge relaxes, right? But you know that density correlate, because in this case, you see how density. It's one of the correlation functions which you can relate to the usual retarded correlation functions, like an integral of retarded correlation function. Then from charge correlation, you can infer conductivity. So that's kind of, so you can get to conductivity through these tools which are more natural to cold atom systems.
Along this fragment. So is there some effort looking at some scaling?
Well, we already saw scaling with temperature. Krista mentioned it, right? So omega over T, so let's say I showed you experiments on the observing Higgs boson. So one of the signatures that this was being excited is the Higgs boson was the scaling of absorption at small frequencies, which is omega squared. So yes, you can do such measurements.
Is the geometrical string model and the platforms actually being powerful in the sense that you could possibly combine some chimera and the crossover?
It's a good question. Good question. Like philosophy is rather different, I would say, because the philosophy of RVB is sort of like when you dope, you suppress sort of spin correlations, magnetic order everywhere in the system. Whereas geometrical string model, it's more like, oh, this suppression of magnetic correlation is very low, which is happening in the vicinity of a double neighborhood. Whether you can find some middle ground is an interesting question. I mean, you can say that, like to some extent, we're doing like, oh, well, it's real actually. Give credit, Annabelle and Fabian are doing this because what you can do is like when you construct this geometrical string, as I said, you do not start with a picture of perfect magnetic relations. You assume that there is some background of magnetic correlations, whatever they are. You can take them from the data, you can take them from Monte Carlo. So you can then take them from pi flux RVB. So yes, so things like this you can do. But then pi flux, so far we have seen that pi flux RVB, let's say it has some, no, you can do, like actually it's known that like exactly at half fillings, I mean, there are certain mean fields which require still like both broken symmetry and some kind of pi flux to get the best description of the data. So this is, say, in the work of Dima Ivanov and Patrick Lee. So some kind of pieces are there which try to combine.
So I had a question about the quantum system.
Mm-hmm.
So in simulation, say starting of dynamics of get a sense of where the quantum factors comes because you have low complexity. There's in this case of infinite temperature correlation functions, it's harder to see where you're getting the quantum factor.
So yeah, okay, it's like the naive, like a simplest answer would be as follows. Well, basically what infinite temperature means is that you have to compute the spectrum over the entire Hilbert space. You have to diagonalize a matrix which has a size of the entire Hilbert space, which is exponentially large, and that's why it's hard. So what we're doing, instead of sort of like, so computing this Excitations spectrum in the simplest way, would be an exponentially hard problem because you have to diagonalize a huge matrix. Whereas with this quantum simulation, you can show that it's only like n squared log n. Yeah. Well, I mean, you can, it now depends. I'm sure people who do like NMR for living, they will not agree with me because they don't really diagonalize exponentially large matrices. So because they would say, well, nature is kind, and therefore usually individual spins, they don't really talk to every other spin in the problem. So the way they solve their problem is they just say, well, let us write chain of equation, and basically the more coupled high order terms you keep, that's the more neighbors you allow, and then they just truncate like at 6 and 7, and then they claim that's enough, right? So they by brute force force it to be polynomial, but then it turns out that first of all you don't know where it gives you error. Secondly, that there are systems which, okay, I have some examples where it's known that which are hard. So it takes really like kind of many hours of calculations just to do this kind of solving this classical equation, coupled classical equations of motion. So maybe I'm not answering your question exactly, but right, yes. Right, but what you can, okay, sorry, I don't have the slide. Because naively you would also say, oh, look, it's so infinite temperature, it's so classical. Let us just do Landau-Lifshitz equation. That's probably the most striking. Landau-Lifshitz or even truncated Figner, they're completely wrong. Even for like simple systems like for spin, because more or less the complexity of this problem is the same as like if you have one clean qubit coupled to like infinite temperature ensemble, and you can show that this model you can no longer simulate classically.
Yes, the string model. I remember back a long time ago, Stuart Trugman did lots of numerical simulations. Exactly. At the time, it just wasn't convincing that there were these strings. I just wondered if there's anything different.
Yeah, I think. Yeah, what is better is that now we have snapshots. And so now we can actually, so what Annabelle and Fabian have done, they really sort of extended the work of Trugman. It's in the same spirit, just taking it kind of more seriously. And probably another difference is that when you start constructing the string, you actually have to start with a state that already has quantum and thermal fluctuations. You do not start with a classic antiferromagnet. So that's crucial. I think that's the part which, let's say, he did not. I may be wrong, but at least the work I remember, I think so. Kind of the spirit is the same, but you still have to add a few extra pieces. Well, roughly, it seems to coincide. We can get the size of the colorants, and it's kind of within factors of 2 and so on. It's roughly where these polarants start touching each other. So because the model, the way we constructed it, we really assume that this is like basically polarants just sort of do their thing individually, don't talk to each other. Once they start touching each other, obviously it fails.
But to what it could be 2 parts. First of all, what is the prospect for lowering the temperature further? In the United States, as you know, 10 years ago, great things were claimed for using quantum simulators and simulators that I can see, and we no longer need to really make materials anymore.
I don't think anybody claimed that, that you will not need.
Close to that. But 10 years have passed now. To what extent is it possible to go, for example, down to 10% of J? Is it be anywhere closer to that?
Okay, first let's have I think I believe that at least the way I would formulate the question, have we gotten new insight into the Fermi-Hubbard model from cold atom simulators? And I try to convince you that we did. So we can see magnetic tolerance, right?
Right.
So
bring me to my second question, could be to what extent does that picture hold as you go down to those lower temperatures? For example, you could imagine exponentially suppressed Fermi temperatures so that once you go below those temperatures,
Sure.
you re-establish a simple parametric, for example. And so to what extent, I guess it's at the moment you're kind of in the range of high temperature series.
Well, okay, I guess I try to show you that actually as we go to higher doping, it actually looks like weakly interacting from a gas. The temperature is still high, so that it's not exactly from a liquid, but you see that like simple Linhart function, RPA type description work. So we can establish there is a regime of the Fermi-Hubbard model where Fermi, like perturbative approach in interaction is valid. We can also establish a regime that for smaller doping, it's not working. So at least my take on it now that in this underdoped regime, temperature is low enough that we can see physics of this polarons. It's not yet low to see self-arpenization of polarons unless we play the tricks like mixed dimension, which I showed you. Now, I'm pretty confident that we will see more progress on cooling. I mean, it's okay, it's taking longer than we expected, but it's coming, right?
What is the base temperature of the experiments that you've done at?
Like, at the moment, I'd say probably like 0.7 J. So it's low enough, you know, that to see all my, like basically, again, so I don't have a slide, but say when they measure, again, these are measurements from a couple of, maybe already 3-4 years ago by Marcus Greiner. So they measure spin correlation in a 2D system and doped system. So the correlation length is already as big as the system size, which in that case, you can say, oh, it's 10 by 10. So, okay, it's not a large, but it's 10. Like, so it, like from the point of view of magnetism, you do not gain much by lowering the temperature. But of course, you gain more by looking at the doped system. But I think, you know, at least to my, okay, maybe I think we should think about cold atoms as not a replacement of condensed. It's very complementary information. Say this multi-point correlation function, right? It's something that we simply cannot measure, right? And okay, I didn't have time to talk about you. You remember this exact solution of TJ model in 1D, right? That you can show that if you if you remove all the holes, you will see that spin correlations do not depend on doping. Of course, like it's unthinkable in condensed matter. You cannot like take an image and remove all the holes, but that's what has been done. So that's why, on the other hand, transport is not easy. So that's why we get other type of information about strongly correlated systems from cold atoms. So I don't know if it answers your question.
Could you just follow up on this high temperature I've looked at more of the Wick-Heights data and the food rates. The Wick-Heights, a lot of things happen at low energies for temperature. If you go to 200 MeV, everything looks like under that relatively dispersive excitations see in the magnetic measurements.
Yes.
My impression is that in the food rates, you can do Wick's measurement for higher excitations. The change as a function of doping is not that dramatic. So I wonder when you make a statement that as you go to higher dopings, it looks like the gas like.
Again, you see, I can let the data speak for itself, right? You see, if you do RPA type calculations, it fails around 30% doping. You know, like higher than 30% RPA works. Below 30%, it doesn't work at this temperature. Around like 0.7 J.
I can see how these quantum simulators are useful in the sense of being able to design symmetries of different classes. I was wondering to what extent you can actually design different symmetries at a different site, say,
Well, that's something that people have been thinking about. Sure, but let's say so the easy things, well, not easy, like easy for a theorist, but not experimentalists. They can go from alkali atoms to alkaline earth, and then they can get SUN with like huge n, like n equal 11. So that gives you, of course, completely new types of phases once you go to SUN with large n. Then people have been thinking about, let's say, P-wave. I think Ryan, I think you worked on P-wave orbitals, right? Cold atoms. Yeah. So there are people in this room who actually worked on adding some of the non-trivial orbitals to cold atoms. And experimental, I think people in Hamburg are pursuing this quite actively.
There are no more questions. So let's thank Eugene for being on. And the second talk is
Tomorrow.
Thank you. Okay, so I don't know why.